Don Machholz, and you are listening to Looking Up with Don. This is the Looking Up with Don podcast, episode number 72, for the week of May 19th, 2021. The related website for this podcast is donmachholz.com. That is spelled DONMACHHOLZ.com. 2 H's. What's up in the sky this week? As our week begins on Wednesday, May 19th, the moon is half full, being first quarter on May 19th at 1900 hours Universal Time. It is in the evening sky, and for the next week will continue to get brighter and bigger. By next Tuesday, May 25th, the moon will be almost full. Actual full moon and a total lunar eclipse occurs the next day, Wednesday, May 26th. We will discuss that in more detail in a couple minutes. Early next week, on Friday, May 28th, the planets Venus and Mercury will be very close together in the evening sky. This is known as a conjunction, and they will be less than a half a degree apart at their closest. This week, as we lead up to the event, they can both be seen in the western sky before the sky completely darkens. Over the next week, Venus moves about 1.2 degrees upward in reference to the background stars, while Mercury, much fainter than Venus, climbs more slowly, then starts heading south. Mercury will be a few degrees above Venus most of this week. We will talk more about the conjunction next week, but watch them this week as they approach each other. In our morning sky, Saturn rises about an hour after midnight and Jupiter rises about an hour after that. The nova in Cassiopeia is barely visible to the unaided eye if you have a dark sky. With the moon in the evening sky, get out this week in the morning and see it. Use a telescope or binoculars to locate it using podcast 72 map 3, and then try to see it with the unaided eye. It is right next to the open star cluster M52. Nova this bright are rare, so do not miss this opportunity to see one. Okay, we have a total lunar eclipse coming up next week. This is when the very full moon goes into the Earth's shadow, and the only light striking the moon is refracted light, light bent by our atmosphere. The moon will darken and turn red or orange. Half the world can see this one. From the time the moon begins entering the Earth's outer shadow, goes through the inner shadow, and then exits the Earth's outer shadow on the other side, 5 hours will elapse. Some of you will see the whole eclipse, all 5 hours, while others will see only a portion of the lunar eclipse, and a few of you won't see any of it at all. The moon will be in the southern sky, just a few degrees from the globular cluster M80 in Scorpius. As the moon moves through the Earth's shadow and the moon gets darker, you might see some portions of the Milky Way. One more thing to note. The moon will not be passing through the center of the Earth's shadow, but instead it skims through the northern portion. So the greatest effects will be on the southern half of the moon, which will be closest to the center of the Earth's shadow. This also means it's one of the shortest total lunar eclipses ever, just 18 minutes long. All right, the very beginning of the eclipse. Anyone who can see the moon can see these stages. The first stage, when the moon starts to go into the outer shadow of the Earth, is on Wednesday, May 26 at 0846 Universal Time. Now, Eastern Time, that is 4:46 in the morning. On the west coast of the United States, that's 1:46 in the morning of Wednesday, May 26. All of the continental United States, Western and Central Canada, Central America, and most all of South America will have the moon above their horizon at 8:46 Universal Time. What will you see? Not much, as the changes to the moon will be subtle at first, and you probably won't notice much for at least the first half hour. For some of you, the moon will set before much happens. Well, there will be other eclipses. All of New Zealand and most of Australia will see this first stage, and they will end up seeing the whole eclipse in the following hours. An hour later, at 9:45 Universal Time, the moon begins to enter the Earth's inner shadow, and you'll notice it getting darker on its southeastern limb. The shape of the Earth, round, will be projected upon the moon. The Earth is about 4 times larger than the moon, and you can sense that by looking at the shape of the Earth's shadow on the moon. You won't see much color on the moon at this point. Much of the United States and most of South America will see this stage. All of Australia and New Zealand will see it, and the moon will be then just rising in Japan. The moon takes a long time to travel far enough to be completely inside the Earth's shadow, nearly an hour and a half. At 11:10 Universal Time, this occurs, and we say the lunar eclipse is, at this time, total. The western half of the United States and the west coast of South America will see this as the moon is setting in their western sky. You will need a low western horizon to see this well. The east coast of Asia will also see this phase as the moon is rising in their eastern sky. Things don't change much in the next 9 minutes as the moon moves to mid-eclipse at 11:19 Universal Time. At this point you might say, "You call this an eclipse?" Good call. The moon is barely inside the Earth's shadow. The north side of the moon will be much brighter than the south side. And the southern side of the moon does not even reach far south enough to reach the center of the Earth's shadow. A better placed moon would make for a better eclipse. With the moon low in the sky, this might make for some good photography. Give it a try with your cell phone. The people on social media do this all the time. At 11:28 Universal Time, the total phase ends as the moon begins to move out of the Earth's shadow. The northeast limb of the moon will emerge first. By 12:53 Universal Time, the moon will be completely out of the Earth's inner shadow, and by then it will have set for all of South America and nearly all of North America. The moon will be completely free of the Earth's outer shadow by 13:51 Universal Time. So there you have it. A total lunar eclipse next Wednesday morning, May 26, for those in the Western Hemisphere, and for those in the Eastern Hemisphere on the evening of Wednesday, May 26. Will you be able to see the International Space Station this week, which for our purposes begins Wednesday, May 19th through Tuesday, May 25th? Last week, we could see it multiple times per night. This week, less so. This week we have 6 zones. All you need to know is your latitude. North of 64 degrees north, you'll not be able to see the ISS at all. Between 35 and 64 degrees north, it will be in your evening sky all week long. It will also be in your morning sky for most of the week. You might be able to see the International Space Station 3 times in one night. From 18 through 35 degrees north, the ISS will not be visible at all this week. The equatorial region from 30 degrees south to 18 degrees north, the ISS will be in your morning sky. Those near the south end of this band, near 30 degrees south, will see it all week in your morning sky. Those north, approaching 17 or 18 degrees north, will see it only the first few days in your morning sky. From 35 to 30 degrees south, the International Space Station will be in your morning sky all week long, sometimes twice per morning. South of 35 degrees south, the ISS will be in your morning sky for only part of the week. To determine where you can find the International Space Station traveling across your sky, go to the website heavens-above.com and enter your location. Then click on ISS. Now for the astro class. The brightness of an astronomical object is expressed by something called magnitude. Two things to remember about magnitude. First, the smaller the number, the brighter the object. And the larger the number, the fainter the object. A star that is of magnitude 2 is brighter than a star of magnitude 4. When an object is really bright, it might have a negative number, such as the planet Venus at magnitude minus 4.8, the full moon at magnitude minus 12.7, the sun at minus 26.7, and the brightest star Sirius, magnitude minus 1.46. The faintest star you can probably see with the unaided eye is probably about 6 magnitude. With binoculars, you can go to magnitude 8 through 10. With a telescope, magnitude 10 through 16 generally. The Hubble Space Telescope, taking images which gather light over hours of time, can image objects at about 30th magnitude. Secondly, magnitude is on a logarithmic scale, and each magnitude is about 2.52 times brighter or fainter than the adjacent magnitude. So a 2.0 magnitude star is 2.52 times brighter than a 3.0 magnitude star. And that 2.0 magnitude star compared to a 5.0 magnitude star, the difference is 2.52 times 2.52 times 2.52, which is about 16 times brighter. A 5 magnitude difference is 100 times different in brightness. For extended objects such as galaxies, clusters, and comets, we estimate the total integrated magnitude. That is, how bright the object would be if all of its light were squeezed down to a single point. But in reality, it is not. The light is spread out over an area. That means that a comet that is 10th magnitude will appear fainter than that of a 10th magnitude star. And sometimes the least amount of light pollution or twilight will wash out a comet so that it cannot be easily seen at all. Finally, we're estimating and calculating the magnitude of objects as seen from the Earth's surface. If an object is closer to us, it would be brighter. And if it were further away, it would be dimmer. How much so? If it is double the distance from us, it would be 4 times fainter. And if it's triple the distance from us, it would be 9 times fainter. The brightness varies as the square of the distance. The brightness of the object as seen from the Earth is known as the apparent magnitude. If we know how far away the object is from us, we can calculate what is known as the absolute magnitude. For stars, the absolute magnitude boils down to how bright the object would be if it were 33 light years from us. This is known as the absolute magnitude. As for distance, perhaps the closest astronomical objects that we can see are meteors as they burn out in our atmosphere at a height of 60 to 80 miles, about 100 kilometers. Further up and beyond that, we have aurora, that's northern and southern lights at about 100 miles or 160 kilometers. Next up are the artificial satellites orbiting the Earth a couple of 100 miles up, with some of them 22,000 miles out. The moon is about 250,000 miles from us. That's about 400,000 kilometers. Most of the major solar system stuff is within about 3 billion miles of us. That's about 4.8 billion kilometers. The solar system extends out farther, but the objects you see will more than likely be within 3 billion miles of us. When it comes to the distance to the stars, we make a quantum leap. No longer are we measuring in miles, but instead we're using something known as a light year. A light year is the distance that light travels in 1 year, traveling at 186,000 miles per second, which is fast enough to go around the Earth 7 times in 1 second. This translates to 300,000 kilometers per second. The closest star to us besides the Sun is 4 light years away, and the stars we see with the unaided eye in the night sky are typically between 4 and 3,000 light years away. Open star clusters and nebula are typically between 400 and 10,000 light years away. Another deep sky object known as globular clusters are between 6,000 and 50,000 light years away. All of these objects are in our own galaxy. The next big step is the distance to other galaxies. Our galaxy, the Milky Way galaxy, has a couple of small satellite galaxies about 600,000 light years away. But most galaxies we see with our unaided eye, binoculars, and amateur telescopes are between 2 million and 200 million light years away. Large telescopes can see objects up to 13 billion light years away. Next week, I'll discuss the coordinate system of our sky, known as right ascension and declination. I'm working on several astronomy projects at this time. Sure, I do this podcast each week, and I continue to visually comet hunt. But these are other projects, and they'll result in writing 3 books that have to do with visually observing deep sky objects. There is a lot of interesting research that goes into writing these books, and these are exciting times for me. To recap the podcast, what's up this coming week? Mercury and Venus close in on each other on our evening western sky. The moon is dominating the evening sky. The nova in Cassiopeia is bright. Get out there and see it. And at the end of this week, May 26th, we have a total lunar eclipse, one of the astronomical highlights of the year. You have been listening to Looking Up with Don, podcast episode number 72 for May 19th, 2021. I'm Don Machholz. Once again, the related website for this podcast is donmachholz.com. That is spelled DONMACHHOLZ.com. 2 H's. You can contact me at dontheastronomer@gmail.com. Once again, that is dontheastronomer@gmail.com. God willing and pod willing, I'll be back next week for another episode of Looking Up with Don. We will discuss what's up in the sky, cover the conjunction of Mercury and Venus, and learn about the coordinate system of the sky. All that and more. Thank you for listening. See the sky this week. I'll see you next week.